Welcome everyone. This is the second part of my milliometer video. So in the first part I built this high precision milliometer, and I could not test it obviously because I haven't included the Arduino Nano. So there was no microcontroller to read the AD converter and convert the voltage and current into resistance and send it to the serial port or put it on a display like it will be in this case. So this part will be about finishing up. So I will show you what is inside this enclosure, because as you can see now everything is in an enclosure. And then I will go to my computer and show you the source code, and I will explain you the main principles of this AD converter, how it receives the information and how we should convert that information into a human readable voltage value. So in the previous video I already started to show you these PCBs, and I designed these PCBs and then they were manufactured by the sponsor of this video, PCBWay. PCBWay is a PCB manufacturer with many relevant services which can be useful to you if you would like to replicate, for example, this project. Apart from making the PCB, for example, they can also assemble it for you, as well as they can source the necessary part, which can save you from a lot of headache. And they also have other manufacturing services, such as machining and 3D printing, both plastic and metal 3D printing, so they can make any kind of custom parts for you. So you should head to PCBWay.com, upload your relevant files, customize your product according to your needs, and just order whatever you want. So I hope that you will like their products and services, and now let's see what we have more than these PCBs. So we have these PCBs, and I used one of them and built it into a circuit which can be found under this enclosure here. So I will try to carefully separate everything and show you what is inside this box. So now, as you can hopefully see, we have the circuit here assembled, and then we have 6 cables, or 3 pairs. This set of cables which I'm touching right now is for the power supply, and then this set of cable for providing the current, and these 2 cables go to the top 2 BNC connectors, so positive current, negative current. And then we have the green plus black here, which go to the bottom BNC connectors, positive voltage measurement and negative voltage measurement. And that's all. And you can see this 4 cable ribbon cable or jumper cable. Those are the connecting cables for the OLED display here. So I2C connection, and basically that's all. And then these BNC connectors on the top of the enclosure go and connect to these BNC connectors. And then we have these special 4-point sensing clips. So on the red side we have the positive current source and the voltage measurement, and here we have the negative current source or sink and the voltage measurements negative side as well. So when we clip this clip on, for example, the pins of a resistor, an unknown resistor, then the resistor will be supplied with 100 milliamps, and based on the voltage drop generated by that 100 milliamps across the resistor, we can measure the voltage with the 2 other sides of the clip, and we can convert those measurement values into something human readable values. So also I haven't shown it to you, but there is a DC jack which provides the power supply for the internals, and I also made some small 3D printed parts, because these standoffs inside the enclosure are not perfectly aligned with the holes, because I did not design this PCB to be compatible with this box or any box. So I had to make them, but now it's perfectly standing there and it's very solid connection. And just before assembling this board and showing you the measurement, I just quickly want to go through this PCB, because if you watch this video for the first time and you haven't seen the previous video, first of all check it, it's up there in the corner, you can click there, but you can see the principles of this PCB as well. So what we have here is that here comes a voltage regulator, which provides 5 volts to the board, except to the Arduino Nano. Why? The microcontroller doesn't like to receive 2 voltages, one from an external source and another from the USB. So if I want to use this simultaneously while I'm connected to the computer, then I don't want to kill the Arduino by providing 5 volts from 2 sides. So I just decided to provide the 5 volts only via USB. But if you are sure that you will not use them at the same time, you can do some wiring through this PCB, and then you can resolve this issue. But the 5 volt voltage regulator provides 5 volts to all the components except the Arduino. And then on this side, we have the most important part, or one of the most important parts, which is the current source and the shunt voltage reference. So this U2 chip is the shunt voltage reference, and what it does, it clamps one of the pins of the current source to 1.25 volts, and then the current source, U3, will generate the current based on this voltage and based on this set of resistors plus one of the variable resistors or potentiometers, RV1. And then this system, so the set of resistors, the shunt voltage regulator and the current source, we will generate 100 milliamps on these 2 pins here. And then if we attach this to an unknown resistor, we will have a voltage on this resistor which we can measure. And what we have here, first the voltage comes in and it goes to a precision differential amplifier, and this does a 10 times gain on the voltage. So if the voltage on the resistor is 100 millivolts, then on the output of the amplifier we will have 1 volt. So 100 millivolts goes to 1000 millivolts or 1 volt. And this amplifier needs plus and minus 10 volts. So on the bottom of this circuit we have a charge pump converter which takes the 5 volt input, only plus 5 volt, and converts it into plus and minus 10 volts. So this plus and minus 10 volts is traveling through the board to the precision amplifier. And then the output of the amplifier is connected to a 24-bit AD converter. And this AD converter obviously converts the analog voltage into some digital values, and these digital values are being forwarded to the Arduino Nano. And the AD converter also needs a reference, and this chip here, the U7, is a voltage reference chip which provides 4.096 volts as a reference voltage for the 24-bit AD converter. And with this, the circuit is complete. And if we connect the Arduino Nano to the board and display, and we use my code that I developed, then we can use this thing, and I will show you how it works. And one thing I haven't mentioned is that we have another set of resistors and the potentiometer, which is in relationship with the precision differential amplifier. What you can do with these things, especially with the RV2 potentiometer, is that you can trim and set the input voltage to 0. So while shorting the inputs of the voltage measuring side, you have to turn the potentiometer until you read exactly 0 volts. And then you sort of balanced out the input of the precision amplifier. And that ensures that the AD converter will read precise values. So now I just assemble this box carefully, and then we do a few measurements to be precise, and see what is happening with the readings. So I just have to squeeze everything in the box, something like this. So we are done. So we have 2 red cables or red connections, and it doesn't matter which we use, but we know that the BNC connector 1 and 3 are the positive sides. So I connect to them first, just to make sure that the positives are connected. And then this is the negative side, so it's indicated with this black thingy. So that is the second and the fourth piece here, and the BNC connector. So this is done, and I just have to make sure that you will see the display properly. So I just flip the cables and pull them like this. So the display will show you something very soon. I connect the power supply, so this will be the 9-volt power supply for the circuit. And then I connect the USB to a mobile charger, which will provide power to the Arduino. So it works. We have the welcome message. And now we see a dummy value because there is no resistance connected to the clips. So here is the clip. And here is my two test resistors. One is a 1 ohm and another is a 2 ohm resistor. So let's come and check the first 1 ohm resistor. So I just apply the clips, and I have to wait a few seconds to have the 10 readings and have them averaged. So we are reading 101.85 millivolts, and then that is converted into milliohms. So this is 1019 milliohms, or 1 ohm, but we can confirm it with this multimeter. At least I read the voltage, and we can see if the voltage is the same on that side. If I can find the connection. So that is reading 102.40 something. So it's close enough. And as I mentioned, we can trim both the current source and the voltage input, and I haven't yet done that. So of course we will not measure the most precise values, but for my purposes this is, let's say, close enough. So we can see that we measure roughly the same values. And now, for the sake of fun, I just jump to the other resistor. So this is twice as large, so it's 2 ohms instead of 1. And we can see in a few seconds what is the value, whether this is a 2 ohm resistor for real or not. And this is a bit lower than 2 ohms, you can see, 1925. And then let's see what is this reading does here. And that is reading 194.25 millivolts. So actually it's just 50 millivolts of as compared to this measurement here, 50 millivolts lower, so that's close enough. But yeah, as you can see, it works. So basically I fulfilled everything and I completed this project. And the fact that we can see the proper numbers on the display, or we can see numbers at all, also indicates that the programming was successful. So this is basically the project. And now we will go to my computer and I will explain you the code thoroughly, so you will understand how to read this AD converter and how to convert the values from a voltage into a resistance value. So let's go to my computer. So let's check how this code works, and this will be a short explanation because the code is actually really simple. So first of all, we need the SPI library because of the AD converter. It communicates with the Arduino via SPI. And then we need the wire or I2C library because of the display. And then this is a copy paste from an example from Adafruit, because I have the display which uses this SSD 1305 module. So then we just use the corresponding library, and then we initialize display something like this. And once we are done with this part, I started to initialize and create a few variables. So we have the chip select pin, and that is obviously the default pin, which is the pin number 10 on Arduino Nano. And then I have the raw ADC data, so that's the data from the AD converter before any kind of conversion and stuff. And then another kind of raw data, and this is even more raw than the raw ADC data, is the register data. So this is actually the value which we directly read out from the AD converter, and this is the data which is being combined by bitwise operators and so on. You will see how it works. And then obviously we need to store the voltage somewhere. The current is fixed, which is 100 milliamps, so I just gave the value of 100 to it, and I will never change this. And then we have the resistance. This is what we will calculate based on the formula for Ohm's law. And then I have a Vref, which is the reference voltage, and we know from the voltage reference chip that that is 4.096. And this value is used when we calculate the voltage based on the ADC data. So we come to the setup, and this is the part of the code which runs only once when we start the Arduino. So we have the chip select pin, and that has to be defined as an output because we want to switch it. And then we immediately switch it to high. And then we need the SPI for the ADC, so we just set it up in this kind of method. So we start with the SPI begin, and then we set the bit order and MSB first. So the most significant bit comes first, and this is because this is how they described it in the datasheet of the AD converter. So it sends the MSB first, and then we get the LSB as the last byte, or in fact the last byte also contains some sub LSBs, but we don't go that deep here. And then there's just a clock division of 16, which means that the SPI will run at 1 megahertz. And as I said, we will also utilize the USB, so I have to start the serial, and then I just use this low speed, low baud rate. It's not like it matters, but now I just use 9600. Again, this part is coming from the Adafruit library, and all it does, it just waits for the display to respond. And if it doesn't respond, it throws an error message, and that's all. But luckily, I don't get this message, so the code will go here. And this is a very basic, let's say, welcome screen. So we have 4 lines available with this text size equals 1. I just use the normal color in this case. So in this context, the white means that the display will use the pixels, so it will turn on the pixels, because actually you can define this as black, so it will invert the display sort of, and that will mean that your characters will be those pixels which are not lit, and all the other pixels are in blue in my case because I have a blue display. And this is just to put the cursor on the top left corner, and then we start printing. And since I use the println function, everything will be put in a new fresh line. So you can see that we fill in 4 lines. And this just puts the things in a buffer, but once we run this display.display function, then that will actually put it on the display, and we will see this welcome message for 3 seconds. And now comes the loop part, so I try to clean it up, and what we do here is first we calculate the voltage. So raw data comes in, we convert it, we process it, and we get the voltage from the voltmeter. And then now we know the voltage because we measured it, we know the current because we determined it. So we control it by using the circuit. So we make the current source to produce 100 milliamps. So then Ohm's law is applied, and we can calculate the resistance. And finally, we print the values on the display. So let's see how the voltage is being obtained. And that's basically the most, let's say, important part. And first of all, we go to the calculation, and then we will go to the AD converter part. So here it's very easy. I just have the raw data, which is being sent by the AD converter and being processed by the Arduino, but it's still in a raw format, in a sense that it's just bits and bytes, but no real value, not a value which can be read by a human easily. And then we have the voltage, and I put both of them, I make them 0 because we want to start with a clean set of data, because we will use some summation and stuff, and we don't want to, for example, reuse previous data. And then this is the averaging, which I mentioned already. I just run 10 readings, and what it does is that it keeps adding the reading of the ADC to this raw ADC data. So at the end we will have 10 times the value, and that's what we will use for the further calculations. And here I have to do a delay because there is a conversion time, and if you open the data sheet for this AD converter, you will see that this value is around 130 something milliseconds. But for safety and everything, I just kept this as 200 milliseconds, and everything is working well with this, so I'm happy. And once we have the sum of 10 readings, we divide it by 10, obviously, so we get the average. And then I immediately print it on the serial port, so I see what the Arduino sees. And after this, I calculate the voltage. So what happens here is just the typical formula which we have. So we have the raw data which we read from the AD converter times the reference voltage divided by the resolution of the AD converter. And then I have a times 100 here because I want the voltage to be stored in millivolts. And why it is 100 instead of 1000 is because we have an onboard precision differential amplifier on the PCB which does a 10 times gain. So actually the voltage which reaches the AD converter is already multiplied by 10. So when, for example, the AD converter sees 1 volt, the real voltage on the resistor is 0.1 volt or 100 millivolts. So that's why we just need to multiply here by 100 instead of 1000. So I hope that this is clear. And then in this part, we saw that actually we use this read ADC function, which returns with a value, and that returning value is the pure clean reading of the ADC. And how does this work? Let's see. So we have this function which communicates with the AD converter, and I broke it down into very details. So if you are totally new to this AD converter or totally new to AD conversion at all, you will probably read the basics and understand the basics here. So what the LTC-2400 does is it does the conversion, and then it enters into a sleep state, and it stays in this sleep state until we, the users, manually pull the chip select pin low. And after we have the chip select at low, the AD converter starts to spit out the data on the SPI line, and then we will read those numbers 8-bit or 1 byte at a time. So this will be repeated 4 times in total. So we have 32 bits of data. And this is how the data looks like. I just split it up into 4-bit chunks because this has a certain structure. So we read from left to right, and in the A package, so the first 4 bits communicates or tells us the sign, and it also tells us the input range and the conversion state. And this conversion state is what we need. This is the end of conversion bit, basically. And when it is low, the conversion is done. So that means that when that thing is low, we can read the rest of the data, and we can use that data to get the voltage. And then in this kind of package, from B to G, we have the conversion value, a 24-bit number, and that is starting with the MSB, which is here, the most significant bit. And then in the H package here, we have the sub LSB parts that can be discarded. As I said, we don't go too deep with this AD converter, so we don't care about this LSB. So what the third point said here is that we have to pull the chip select pin low. So we do that. And once we did that, we start reading the master in, slave out pin. And what we will do with that is that we will actually wait for the end of conversion bit to go low, because as long as this doesn't happen, the digital read equals 1 will be true. So the while loop will keep the code in this line, basically. And then once the end of the conversion bit, this guy here, which I highlighted, goes low, then this becomes false. So when this is false, the code can continue its way down here. So we make this 0 to have a clean start. And then we start to build up the register data variable from the numbers which are being received from the SPI line. So first of all, we read the first byte. And at the end of the comments, I always put the, let's say, illustration of this number. And what we see is that we start to fill in from right to left. So then we have 8 numbers already here. And as we said here, up here, we need to get rid of some of the numbers, and that is basically the A package, because that only contains information. So that's why I put this as A here, because we have to get rid of that and it's easy to visualize. And how we do that is that we use the register data variable, which we already obtained numbers, and we use the bitwise AND operation, and basically combine this with this number. And what this means is that if you put the two numbers on like top of each other, wherever you have ones, you keep those numbers, and wherever you have zeros, you throw away those numbers. And that will result this kind of ending where we just keep the, let's say, B numbers. And I just made the first B here capital. So you can see that that is the most significant bit, the bit 27. And now we have to shift the register data to the left by 8 bits, because we need to receive the next bit. And this will be the result. So you can see that now the first byte is empty again, so we can put the next data there. And that's what this line does. So it catches the new information from the SPI line, and it combines it with the register data. So what will happen is that this number here is being overwritten by the next chunk of data, which I indicated with letter C. And again, we have to shift this. So we have the first part of the middle byte and also the MSB, and that is being shifted to the left. So again, the first byte from the right is free again. So we catch the next data, which is the second mid byte. I call it like that. And now you can see here that that is the D. And again, we shift to the left with this line here. So now this 3 set of bits and bytes is being shifted to the left. So we have this kind of number, and the front of this number looks quite okay. The middle and the middle, the second part of the middle also, but this is empty. And now we finally received the final chunk of the data, the LSB. So then the final number looks something like this. But then if we go back to the data sheet, we can see that actually we can throw away the first 4 bits and the last 4 bits as well. And we just keep the number which is in the bracket. So actually what we can do is that we shift again, but now in the other direction, so from left to right, and then that will actually remove this part. So I should write this here, but what the final result will be is technically this. So we have this kind of number with the last part, and then we have 1, 2, 3, 4 numbers. So what we will have at the end is something like this. And then 1 byte, 2 bytes, 3 bytes. 3 times 8 is 24. So here is our 24-bit number. And actually we have the zeros here because long 32, the long type is storing the numbers on 32 bits or 4 bytes. So we have still a 4-byte equivalent number, but only the first 3 bytes are utilized. And now we are done. So we can pull the chip select pin high, and then the function returns with the register data. And then this register data is used here. So anytime we call the read ADC, actually here comes the read, the register data, and that is being added to the raw ADC data in each iteration of this function. But yeah, this is how the ADC works. So it's quite simple. And it was already simple for me because of this principle, or actually these principles, because if you check my other videos, you can see that I developed my own library for the ADS-1256. And that is also the same. We have to pull the chip select down, and then actually that AD converter has its own data ready pin, but it's the same principle. We are waiting for the data ready pin to change its state, and then we can start shifting out the bits. And after we finished, we just changed the chip select to high, so we indicate that we stopped reading the bit stream from the SPI line. So it's the same. And most of the AD converters work like this. So once you developed your code and strategy, you can apply it to most of the other AD converters. It's very convenient. So now the calculate voltage function is finished, and we can calculate the resistance. So Ohm's law here. So the resistance equals 1000 times voltage divided by current. Why do we have this 1000 times here again? Once we apply the multiplication to the voltage already, but if you remember, I defined the current in terms of milliamps, which means that we need this 1000 times multiplication, so we see the numbers in milliohms. So now let's say all the units are in harmony with each other, and we will see the numbers nicely. And this is just showing or printing the things, and all it does, it prints a message, prints the voltage value, and then prints the unit. And there is a empty line, and we do the same with the resistance. So at the end we will have like 3 data packages, which tells us the voltage, the resistance, and the raw AD data. And actually I can delete these comments because originally I was printing it with the division, but now this division is actually inside the multiplication factors, so it's not needed anymore. So this is done, and now we can print the display, and that is very straightforward. However, it needed some experimenting because I did not know how the text size will influence the position of the cursor, but it's like 5 minutes work, and you can figure it out yourself. But we clear the display, and then we set the text size to 2, because this is the first line where we print out the resistance, and I want it to have the resistance on large letters or with large letters, because that's the most important parameter. At the end of the day, this is a resistance meter, so of course we want to see that value clearly. And then color is still white, cursor is in the top left corner, and we print the text R equals something something, And then we move the cursor somewhere after the R equals part, and then we print the resistance value with 2 digits, 2 decimal digits. And then we return the text size to smaller one, to number 1. We move down to the, let's say, second line, and then we print U equals something something, and then we put the cursor after this part, so the equation or equal sign, and then we print the voltage again with 2 digits, and we move the cursor away from this value because we don't know the voltage and its digits, how much space it will take. Then this is fine, far enough to accommodate a lot of digits, and at the end of the line we print millivolts. And then we do the same practice, same exercise with the current, but here we only have to print a predefined text because the current is fixed. So we just have to write that it's 100 milliamps and it is fixed. And in fact, this could be omitted because we know that this is fixed. So we could move the voltage down with one more line to the same line where we have this. And I don't know if this library allows, but probably I should change the text size to 3. So the resistance value will be shown with really large letters. And then we also see the voltage with some smaller letters, but we don't really need this information here. And finally, after this part, I reset the voltage for some reason, but maybe I had my own reason for that, but actually this is not needed here because the voltage is always reset to 0 before we start to calculate the average voltage. So I just left this here accidentally when I was creating this code. And yeah, after the display is being printed, we go back to the calculate voltage, and then that will read the AD converter again, and everything will happen over again. So this was relatively simple. And you see that there is no timing or no any kind of, let's say, forced delays, except the delay here, which is needed for the AD conversion. And since we read we read 10 values with 200 milliseconds delay, that means that there is at least 2000 milliseconds delay between two display refreshing, which means that we don't really need to worry about it, and we don't really need to put any kind of timer for the display update, because 2 seconds update interval is already good enough to avoid any kind of flickering and things like that. So in principle, this was the second part, and I think I explained everything which I wanted. So first of all, don't forget to visit my website, curiousscientist.tech, because I put all the information there. The source code is there. I put some extra pictures there just to show this thing for everyone. And I also put a link there where you can actually buy this PCB, the PCB only, but of course, if you want, you can also go for the assembly and use PCB-based services, and you then get the fully assembled PCB for yourself. But if you go to my website, you will have the access to everything. You can download the source code. You can also get my PCB from PCBWay, and you can get some additional information and picture. So I hope you found this video interesting. I hope it was helpful. I hope you learned something, and see you in the next video.